Hi, and welcome to a video on the integral test and estimates of sums. In general, it's pretty difficult or impossible at times to find the exact sum of a series. We had talked about if it was specifically geometric or if it was telescoping, like when we use partial fractions, or many of the terms add to zero, then perhaps we can do that. But for the rest of those infinite series, we really can't determine what the sum is. But we must use these tests just to tell us if it does converge or would it diverge. But it won't tell us exactly what it would converge to. Now we will talk about again being accurate within a certain desired level of accuracy at the end of this section, and you'll get to see how we can still approximate it to the best of our ability. So here's how the integral test works. There are a couple conditions to make sure that we can use this, but if we have some infinite sum, so we have some infinite series here with positive terms a sub n, if our function is continuous, so looking at our a sub n there, if it is decreasing, and again, all of those terms are positive, then if we know that the improper integral, remember these? So if the improper integral converges, so does the series. If the improper integral diverges, then so does the series. And so let's look at a couple examples of how to do these. So this is going to depend pretty heavily on your knowledge of improper integrals. And the integral test actually leads us to another test that we like to use, which is called the P-series test. And this is only good when you have something like 1 over n cubed, 2 over n to the 1/3, because I can have any factor or multiple of a p-series as well. And then you have to look at what is that exponent on n. If it is greater than 1, we know our series will converge, and if it is less than or equal to 1, we know that our series diverges. Now this is exactly sort of opposite looking of a geometric series, because in a geometric series I still have this idea of an infinite series here, but instead of my base changing every time, because here your base is going from 1 to 2 to 3 to 4, in a geometric series, my base is staying the same, and my n, for example, my exponent is what is changing. So this would be 1 over 3 to the first, 1 over 3 squared, etc. Whereas a p-series, my base is changing every time. So if it is, in fact, just the 1 over n to the p, for example, that's going to look like 1 over 1. Again, it's going to depend on what our p is. Let's say it's squared. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. And so I can see my base is changing every time, which is what makes it not geometric. And it's not harmonic, but the integral test would allow me to prove the P-series test, but since we see it so often, they just gave it its own test. All right, so let's see which of the following we have. Well, if we write out number 1, again, because these are going to eventually just be all together like a series in the wild, as we like to say, so you're going to have to determine what type of series it is. So I just like to write out the first 3 or 4 terms so I can see that. So in this case, I can see when I put my 1 and 2 and 3, etc. in for n, my base is changing. So I have 1 cubed plus 3 over 2 cubed plus 3 over 3 cubed plus 3 over 4 cubed, etc. So this is not geometric. I had a chance, right, because I thought, nothing is being added or subtracted into each term, but it is certainly not geometric. This is a multiple of the p-series. So in this case, my exponent, or p, is staying the same, but my base, my power, if you will, but my base is what's changing. So that's a p-series. In this case, my p is 3, which means p is greater than 1. And if I look back up to that p-series test, If it's greater than 1, I know my series will converge. And that's it. That's all I can say, is that it's going to converge or converges by the P-series test. You don't identify the sum or anything, okay? So we're testing all these series for convergence or divergence. We're going to tell the test used, that was P-series test, how we meet our condition, that's that middle part there, and then our conclusion will just be converges or diverges. All right, so if it's written out already for us, sometimes it's written as radicals, and we would prefer to see those as exponentially written. So this would be 2 to the 1/3, 1 over 3 to the 1/3, 1 over 4 to the 1/3, etc. And so I can see that, yep, this is a P-series test that we're doing because this is a P-series type series. The P or the power or the exponent each time is 1/3. Again, this 2 and 3 and 4, etc. is coming from the N. And so P is 1/3 every single time, which is less than 1. And so I know my series will diverge. Okay? So let's get into maybe some not so obvious P-series tests. Now, a P-series is simply 1 over, let me write it out for us. So I don't have to start at n equals 1. I can start at n equals 2. Again, the most important part of this series is that it goes to infinity, right? But this one starts at 1, so I'll just keep it the same. So here's my P-series, n to some exponent, right, which we called P. So I can just leave that as P. There's nothing being added. There's nothing being subtracted. There is certainly one term here. And so I cannot say, oh, well, this plus 1's not really all that important. It's extremely important. So it's not a P-series just by looking at it, but again, if you're trying to simplify some of these series, I would say geometric and P-series are probably the two easiest type of series that we're going to study. And so if you can make it geometric or P-series just by separating your fractions out, so saying this over n cubed plus that over n cubed, then I would do that. And so we've done this before. So I just took the first infinite series, or from n equals 1 to infinity, plus the second series, and added them together when I'm done. Now, if either one of these diverges, I would say my series would diverge because infinity plus, something convergent would still be infinitely big. But each test led me to P-series. However, each test led me to that converges solution, meaning that each summation would have a convergent or finite sum. So if you have finite plus finite, that means it's finite, so the whole thing would then converge. All right, so I'm looking at the difference between 3 and 4. So if you need more time on 3, by all means, you can pause the video, but for now we'll move on to 4. The biggest difference between 3 and 4 I see is that you cannot separate this fraction out. You cannot say this is 1 over n squared plus 1 over 1. You cannot use partial fractions because n squared plus 1 does not factor with real coefficients. You're kind of stuck in that regard. So then what I need you to think about is if you took a look at the function 1 over x squared plus 1, is it a CDP? Is it continuous? Is it decreasing? And is it positive? And again, I don't need these three things all the time. I need them from example 1 to infinity. Now I want you to keep in mind the idea of partial sums. I can find the sum from 1 to 5. Remember, we talked about this before. I can write out when n equals 1, this is 1 over 2. When n equals 2, this is 1 over 5, etc. And I can add up the first 5 terms. That's not the problem. The problem isn't necessarily where I'm starting, right? The finite idea in here. The problem is the infinity part. I need to figure out what or will I have a finite or convergent sum as I head toward infinity for n. So if you change this to a 4 to make sure that you are continuous, decreasing, and positive, it is not going to change your end result. If you change this to a 400 to infinity, again, probably not going to change your result, right? Because you're concerned with the dot, dot, dot part. I can find the sum of the first 399 terms. I don't really want to. I don't really want to write them all out and add them up, but I certainly could. So is this continuous, decreasing, and positive for all of these positive values moving forward? And this is. And so the other big question is, can you integrate? And I'm going to do it first just as an indefinite integral, just so you can get used to the idea of, can you integrate in general? And I would say yes, I can. This antiderivative is inverse tangent of x, and I'm going to put the plus c just to be accurate, but I know I'll have bounds here in a minute. So if I can integrate, then this is a perfect candidate for the integral test. Okay? And a lot of people try and avoid the integral test, and I'm going to try to show you as many as I can of the integral test within reason, so you're comfortable with it. You spent all that time learning your techniques of integration. Let's put them to use. So, and this wasn't even a difficult integral to do. You learned that integral in Calc 1. So here's what we're going to do, though. We're going to see, does the integral from 1 to infinity, and I'll fix that in a second, from 1 over, and most of you don't like integrating with respect to n, but we already know what the integral is, so I'll leave it there. Now, I can't integrate from 1 to n. I need finite bounds here. So what we're going to do is we're going to put like a t value, and in front of this, we're going to say limit as t approaches infinity. This idea of putting the t in there, limit as t approaches infinity, was your improper integral idea. Okay? So I have the limit. I introduced the limit, so I'm going to keep it here, right, until I'm ready to evaluate the limit, which is at least 2 steps away here. So I'm going to evaluate my integral. So I already did that. We already know that that's inverse tangent, but now my variable is n, and I'm evaluating from 1 to t. I'm going to put my bounds in. So keep your limit because you have not substituted yet or evaluated the limit. You're just substituting in your bounds. So your upper bound is t, and your lower bound for inverse tangent here is 1. Now you're evaluating your limit. So now I'm going to think, okay, I need to put infinity in for t. Well, inverse tangent of t, again, I'm only going to graph the right-hand side of this because we're going from 1 to infinity, so I don't need the other side, although it's down here. Okay, so if I'm just on a regular, good old Cartesian plane here, this inverse tangent of t, or if you're graphing inverse tangent of x on your calculator, looks like so, and it does level off. And we should know that that levels off at pi over 2. So as x approaches infinity, or in this case t approaches infinity, this is a finite value of pi over 2. Minus inverse tangent of 1, we should know where the sine and cosine are the same, or where the tangent value is 1, and that's at pi over 4. So this gets me a finite value. So when you have calculated the improper integral, you got a finite value. Therefore, the series will also converge. Because you got the improper integral to converge to a number, right? Converges to pi over 4, which means that the summation will also converge. And this shouldn't be a really large jump for you because the whole idea of Riemann sum is that we're adding up an infinite amount of rectangles, right? And heading towards that idea of the antiderivative, talking about the fundamental theorem of calculus. So that shouldn't be that big of a jump to you that the integral test is actually pretty powerful. Now, it doesn't tell us that it converges to pi over 4. The improper integral converges to pi over 4. All that tells us is that because these were the same, right, the improper integral and the integrand and the summation formula there were the same, that it will do the same thing that the integral does. So the series will match it. Okay, so here's two more, and again, I would encourage you to just look at them or pause this or, kind of do whatever you need to do. I'm going to go through this kind of in parts. So if you just look at this from the beginning, there's no adding or subtracting in multiple terms, which usually is really good news because you're hoping for this to be P-series or geometric. But it's not a P-series because my denominator screws that up, and it's not geometric because my numerator screws that up. Because in one sense, the base is staying the same, the e, but the power is changing. That would be geometric. And in the numerator, my base is going to change every term, so that is certainly not geometric. But it's not a P-series because the denominator's not. So I rule those out. Now, it is continuous decreasing and positive, that CDP idea. So I need to think about, before I move too much further, how am I going to integrate? And I'm just going to look, before I even put bounds on, just how would we integrate that? And this is a by parts integration. So this is the whole, well, not the whole, but this is one of the reasons why we have our techniques of integration. So if you let your u be your polynomial piece each time, you are going to have to do by parts 2 times. So I did it once in the red, once in the orange, and got the green answer. Then you're ready to go. So I already know what the antiderivative value is, and so I sort of just hold on to this, right? I'm not going to highlight the plus c part because I'm going to need all of that. So I come over here and I say, all right, I'm going to try this integral test because it's continuous, decreasing, and positive, and I know I can integrate it. So let's try this actual integral test. So I'm going to write the improper integral, so you're introducing the limit, putting in t as a bound instead of infinity. I substituted in my evaluation of the integral, which I like to do kind of on a separate piece of paper or on a side note. I don't necessarily like to do it within my limit, but you can certainly do that. Put your bounds in. So now I'll put t in and put the 1 in, right? And evaluate. Well, when I go to put in infinity, unfortunately, this first fraction here gives me infinity over infinity. And you don't get to make up, oh, well, I know it's going to go to, nope, just do use L'Hopital's rule. I actually had to use it a couple different times, right? And then you'll get to the point where you can evaluate that limit as t approaches infinity. So this problem kind of had it all, right? It has your idea of integration by parts. Then it had your necessity when you're evaluating the limit that you get infinity over infinity, which was an indeterminate form, so I had to use L'Hopital's rule a few times. And I do come out with something really nice, 5 over 4e squared. They will ask you oftentimes, hey, what did you get for the improper integral? So you're going to have to say the improper integral converges to 5 over 4e squared. So because of that, I know the series will converge, period. You don't say the series will converge to, you just say because the improper integral converged to that number, the series will also converge. And then the benefit is not all integration. takes you that long. So if I look at this one, for example, and I think about how am I going to do this? Well, it can't be geometric or P-series because I'm adding terms together. So the only way that I could make that series geometric or P-series is if I could separate it out. And I certainly cannot separate it out because that plus is in the denominator. So unless I wanted to factor it, which I can, I can factor the sum of cubes, but that is certainly not going to make it any better for separating it out. You can try, your partial fraction decomposition and go that route. I'm not saying it won't work, but this is actually a pretty easy antiderivative to do if you write it out. This is just u substitution. And when we're in Calc 2, I feel like I have every right to say just use substitution because we just got done with our integration technique chapter and we had quite a few techniques of integration and they're not necessarily that short, right? They had a lot more work involved. So I introduced the limit, right? This is my improper integral we've already studied. Here's the evaluation of my integral that I do on the side over here. Put your bounds in, and then evaluate the limit. And certainly if you have 1/3 in each, you can factor out the 1/3 of the whole thing. Be very, very cautious when you're using natural logs. I will show you one limit here in a minute, but this one is, I'm going to factor out that 1/3, so it's really natural log of this quantity minus natural log of that quantity that I just circled. So that is the quotient. Remember, natural log of A minus natural log of B is really natural log of A over B. Okay, and so that is infinity over 2, which is still infinitely big, and natural log of infinity is infinitely big. So since the improper integral diverges or is infinitely big, right, that's what its amount is, this series will also do the same thing, and so that series will also diverge. Again, pause at any time or copy down the problem or try to integrate these on your own, but please use these as a resource as you practice some of these integral tests. They're not too difficult if we remember all of our integration techniques that we learned. All right, here, and the last thing we're going to talk about in this section is how to estimate the sum of a series. So you do have a remainder estimate from this integral test. It will tell you how to stay within a desired level of accuracy, for example. And if you'll notice, these rectangles underneath or above, depending on whether you're looking at left approximations or right approximations, might be able to help you kind of understand where this comes from. And so if I look here, I can say that in order to use the integral test, remember we had to be continuous, decreasing, and positive, etc. And I have to be able to evaluate the integral. So I want to know that this converges in the first place. If this has a divergent sum, then I wouldn't even really want to find the error of this series because I would just want to look at maybe a partial sum of that series. So here's an example. Use the sum of the first 10 terms to estimate the sum of this series. And so again, I'm going to first look at what is this series, what is it even doing long term? So if I have 1 over n cubed, this is a p-series, and since p is 3, I know the series will converge. You could also have used the integral test with your just good old integration using power rule, and it will show you the same thing. So, and I'll show you that improper integral here in a minute. So the sum of the first 10 terms, I wrote them all out, 1 cubed, 2 cubed, 3 cubed, etc., all on the denominators. And I added those up. Hopefully I added them up on my calculator accurately. And I just wrote down, a few of those decimals. You can also change your calculator to sequence mode. For the first 10 terms, it wasn't that big of a deal for me to just type them all in. If I wanted the sum of the first 20, I definitely think it would be worthwhile to learn how to determine that sum on my calculator. So there's the sum of the first 10. Now what I want to do is estimate the error involved in this approximation. So I want to come up with, what does this improper integral even look like? So if I go from n to infinity, 1 over n cubed dn, here's my improper integral because I have to say limit as t approaches infinity so I can have a finite bound. And it is just n to the negative 3, so like I said, I can just use power rules, so it becomes negative 1 over 2 n to the negative 2. So I just wrote it as a fraction because that's what I prefer. And I'm evaluating this from t to n. I put my bounds in, and then I evaluated at t approaches infinity. That part is going to be infinitely big that I just highlighted in blue. And so negative 1 over infinity will go to 0. And so this sum will look like 1 over 2n squared. Again, starting at n and going to infinity. All right, so that's what this sum looks like, 1 over 2n squared. So now I know that the remainder has got to be less than or equal to 10 to infinity because I'm going from n to infinity. So 10 to infinity is going to be, I want my remainder to be less than the sum of all that's left. So 1 over 2 times 10 squared would be 1 over 200. So basically what I'm suggesting is that from 10 to infinity, if you add up all of those sort of rectangles there, you're going to get something that is less than 0.005. So I know my sum from 1 to 10 has a level of accuracy within that 0.005. So now we can answer the question, how many terms would be required to ensure that the sum is accurate to within, that's 1, 2, 3 zeros with a 5, so tenths, hundredths, thousandths, 5 10,000ths. So I need to find n so that that remainder is less than that amount. So I'm just going to set it equal to that first just so I can solve that equation. So 1 over the 2n squared, which is my sum from any n to infinity. That's what it's looking like. Again, it's an improper integral, so I'm approximating here. So I can solve for n. So n squared is about 1,000, so n is about 31.6. So I would need 32 terms in order to reach that desired level of accuracy, which means everything that I would be adding on after that is so significantly small that it's not going to impact my sum more than that amount. So I will show you that when we look at alternating series and we write out more of those terms, I think the error will make a little bit more sense when we take a look at the alternating series and write them all out. But if you write out all of the terms as decimals, it might make a little bit more sense to you that you're not impacting your sum by more than that amount. I hope you found this video helpful, and thanks for watching.